Hello everyone, welcome to this video. In this video, I am going to discuss about quantum states. So in the previous lecture, I have discussed about qubits, right? So we understood the general meaning of a qubit. What was the general meaning? That it is the fundamental unit of information in a quantum computer. Okay, we understood it in little more depth and we got to know that qubit is a linear combination, right? Linear combination of the basis states, and those basis states are 0 and 1, right? And this linear combination of 0 and 1 is possible, or it is known as superposition. And the superposition is a quantum mechanics principle, right? So this we have discussed, and also the physical aspect of a qubit we have discussed. That is physically in terms of hardware how qubits are implemented. So this we have understood, right? But in the previous lecture, I just mentioned the term superposition but did not discuss much in detail. So let me start with superposition. Let me give you the analogy and the intuition, and that I will continue for explaining the quantum state. Okay, so let us start with this. So for understanding superposition, I would like to take one example here, and the example is of mixing colors. Mixing colors, right? So when we mix two colors, let us say, what we get a new hue, right? So mixing colors to get new hue. All right, so let me take example. Let us say the two colors are red and green. So if I mix these two colors, red and green, what do I get? I get yellow color, right? Now the thing is that it is not always that I will get a perfect yellow color, right? Why it is not the case always? Because the amount of red that I'm mixing or the amount of green that I'm mixing can vary. Let me take one example. Let us say if I talk about proportions of red and green in the mixture, so that proportion, let us say, for red it is 1 and for green it is 99, okay, or percentage you can consider. So let us say in the entire mixture just 1% is red and rest 99% is green. In that case, what I will get, I will not get a perfect yellow color, I will get a kind of hue, which will be different, right? Yellowish but a different shade I will get. So that I am naming as y1, because it will be some different kind of hue, not exactly yellow. Okay. After that, there can be some other percentages as well. Um, it can be, let us say, 80% of red and 20% of green. In that case, what I will get, again, not perfect yellow color, but a different hue, which I can name as y2. Okay. So similarly, we can keep continuing. Okay. Now, what is happening here is these whatever y1 y2 I'm getting, right, dot dot dot, if n times I repeat the process with different percentages, different proportion, I will be getting n different hues. Okay, so these all different, so what I'm getting different hues. I hope that is clear to you. And why I'm getting different hues? Because the percentages, or you can say the proportions of both the colors are different in each case. All right. So this is one example that we have taken. Now what happens in superposition? In superposition, these two colors, that is red and green, you can just replace with state 0 and state 1. So let us say red is representing 0 state, and green is representing 1 state. So when I said that it is linear combination, so how it forms linear combination? It is basically, you know, like the percentages. What is the percentage? Okay, exactly, here we don't use percentage actually. What we use, I'm going to tell you, but just I'm trying to give analogy here, that how much zero state is there and how much one state is there, that will determine that what state I am in. So that state will be a different state. Okay, again, based on different proportions, I will get a different state, which can be S2, similarly S3, S4. So I hope you're understanding, right? Based on different proportions of 0 and 1 state, I'm going to get different states. How many states I can get like that? Multiple, right? Based on the different proportions. So that is the analogy here. So by this, I hope you understood what I meant by superposition, okay, and what I meant by linear combination. So to better understand, we will now be seeing the mathematical aspect of qubits. Okay, so mathematically, how do we write it? Let me first of all write. So we write something like this. Okay, let us say this is representing one qubit, or we can say a qubit is in a particular state. So this state it is representing. So this is known as xi, and xi is equal to alpha, then 0 like this, plus beta, and then 1. Okay, so now this equation might seem very confusing and difficult, but I will be explaining each part of that. So here, first of all, this is representing a quantum state. Okay, quantum state. Then here, whatever I've written, this one is state 0. I told earlier that there is a different way of writing these states, right? So state 0 is written like this, and state 1 is written in this manner. So these are state 0 and state 1. So basically, if you see this bracket, this is the bracket, right? And inside this, something is there. So that is, so this is going to represent the state. So this bracket is known as kits actually. Okay, kits. And this entire notation that you are seeing, this is known as, this entire notation I can say Dirac notation. Okay, the notation of writing the states like this. Okay, so now state 0 and state 1 is clear. Now let me come to this alpha and beta. What are these? First of all, alpha and beta are complex numbers. In the very first lecture of this series, that is in the welcome note itself, I mentioned that complex numbers is one mathematical concept that will be required in the entire series. It is one important part of quantum computing. Okay. Similarly, linear algebra is there, which is going to come in upcoming lectures. But this is the point where complex numbers got introduced, right? So I will recommend you, if you're not having much idea, then you can have one brief study about complex numbers. So here, alpha and beta are complex numbers. But right now, in this particular equation, what it is representing, that we have to understand. Okay. So alpha is representing the probability of being in zero state. Okay, or I can say probability of 0. Similarly, this beta, now you can understand that beta is representing probability of being in one state. This is what alpha and beta represent. So basically they are what? They are probabilities. Okay, alpha is the probability of being in 0, Beta is probability of being in 1. Okay. Now what does that mean? So again, I will like to go back to this previous example that I took and explain you. So here what happened is, if you take the first instance of example, right? Here, red, I took the percentage of red is 1 and the percentage of green is 99. So what does that mean? That means in the entire mixture only 1% is red and rest 99% is green, right? So now I will get the hue y1. So what do you think? Uh, this y1, this hue will be very close, will be very close to green color, right? To green color. It will be one kind of shade of green, I can say, because just 1% is red, rest 99% is green. So mostly it will be like green only with little bit of different shade. But at one glance, if you see the color and if you say, then you will be saying that this is green, right? Similarly, if I take 99% of red and 1% of green, then directly by seeing that particular hue, you will be telling that this is red color. A little bit different red, but it is red, right? So same thing. So why that is happening? Because of this proportion. So what is this 99% telling you, right? 99% is showing you the proportion of red, right? But in a different way, I can also tell you, like here I'm not actually mixing the colors and showing you, right? But just this 99% is representing what? It is representing the probability. It is representing the probability of me declaring declaring the color as red, the the new hue as red, right? And this 1% is representing what? It is representing the probability, same thing, the probability of me declaring the new hue as green. So what is the probability that I will say that this particular hue is green? It is just 1%. That means very less. The probability is very less, because the probability is very high that I will be calling this new hue as red. Why? Because the percentage is high. So same thing here. Actually, what happens if I'm having a quantum state? Okay, if I have a quantum state, I'm representing it with Q. Okay, so if Q is there, and let us say I'm measuring this quantum state. So after getting measured, the result that it gives collapses to 0 and 1 only. Okay, after getting measured, the result collapses to 0 or 1. Notice the word here, I'm using or. So that means if one particular state will be given to you, okay, and when we measure that state, that what is the state, okay, if we want to identify, we want to measure, then after measuring, the result collapses to 0 or 1. That means end of the day, my final result, what I will say, I will say that either this state is 0 or that state is 1. And how I will be saying it? Based on the probabilities. If probability of 0 is higher, then I will say that the state is 0. If the probability of 1 is higher, then I will be saying that the state is 1. Simple, like exactly what we did here. Just because here probability of red was more, so I called this color as red. Here the probability of green was more, so I called that the new color is green. So the same concept applies here. I hope this is clear to you. So here alpha and beta is representing that. Alpha is representing what is the probability that after measuring, I will say that the state is in 0 state. And beta is representing that after measuring, what is the probability that the state is in 1 state. Okay, so that means from here, one very important point that you have to notice is after measuring, after measuring a quantum state. So after measuring a quantum state, or you can say just the qubit, we measure a qubit actually. So after measuring a qubit, the superposition collapses. The superposition collapses. And the result is either 0 or 1. Okay. So superposition collapses means what? That the superposition, that is, it was a combination, right? But it will no more be a combination. It is either 0 or 1. The final result, that will be either 0 or 1. Like for example, here also, this one, the first one, here 1% red is there and 99% green is there. So that means it is a mixture. But even if it is a mixture, the final result that I said is that I think the hue is green. So end of the day, I'm just calling it green. It is not a mixture, I'm just calling it that it is green. Okay, so similarly here also, after measurement, the superposition, that is the combination, collapses. Okay, and the result that we get is either 0 or 1. So again, here you can see that the behavior somewhat matches with classical bits only. The final result gets into either 0 or 1, not combination, right? So that is what is happens. So you might have again a question that again, then if we are getting the same behavior like classical bits, why this quantum bits, right? So quantum bits, because uh, till before measuring it, when we are measuring we are getting 0 or 1, but till before that we are actually able to represent, uh, in a single qubit we can have all different, all possible states. Okay, so that is the difference. A single qubit can have multiple states. How it will have multiple states? If there are different values for alpha and beta, all those will be different states. So that is how. Okay, fine. So this one we have seen. Now the thing is that here this entire thing I can also represent as alpha and beta in this manner. Like this also I can write. So this is what this is. I think you are familiar with this notation. It is vector notation. Vector notation, right? So that means we can also say that a quantum state is a vector actually. Okay? And vector of what? Vector of alpha and beta. Vector of two complex numbers, you can say. Where again, same thing, alpha is representing the probability of being in 0 and beta is representing probability of being in 1. So this is in short form, short notation. You can write it this way. Okay, so this was the general form of quantum state and I hope it is clear now. Now there can be many possible states which we will be dealing with in upcoming lectures, but till now, in all the lectures we have discussed about state 0 and state 1, right? State 0 and state 1. So these are the two states that till now we are quite familiar with. So let me show you that these states, how we can represent in this direct notation. These are also states, right? So we can represent them in this direct notation or in this vector notation. So let us do that. So first of all, let me take this state 0. So state 0 is written this way, right? So that means this state also I can represent in this manner, right? Now, previously, what happened here, just because xi is written, which is a general symbol, right? So, I don't know exactly what will be the value of alpha and beta because I don't know this final state, what it is. Okay. But now since here we have state 0, so I'm confirmed that the final state, right, the final state is 0. So if the final state is 0, that means what are the probabilities, what are the values, like the numerical values of alpha and beta, that we can try to think about. Okay, so if the final state is 0, that means that means I can say alpha is complete probability, right? Complete, I can say, or it is full. So then this can be written as 1, 0 plus 0, 1. Okay, what does this mean? This means that what is the probability that the state will be in 0? So the probability is full, like probability, any probability if you take, that ranges from 0 to 1, right? 0 to 1. If the probability is 1, then that denotes complete probability. If it is 0, that means no possibility, right? Okay, so same we are doing here. Alpha is equal to 1 here, right? So alpha is equal to 1 means that complete probability, full probability that the state will be 0. And what is the probability that the state will be in 1? So there is no probability, there is no chance, because I know that already the state is 0. So there is no chance, there is no probability that the state is going to be 1. So that is why here it is 0. So I hope it is clear. So from here you can understand that alpha is equal to 1 and beta is equal to 0. Okay, now previously I told that these are complex numbers, so actually you can represent this in terms of complex numbers. One can be written as, although these are looking like real numbers, but we can write it in complex number notation also. So I can write it as 1 plus 0 iota, right? And this beta can be written as 0 plus 0 iota. Okay, so anyway we can represent this in form of complex numbers. Now, so this can also be written as in the vector notation. If you want me to write, then I can write it as 1, 0, right? So this is how actually state 0 is represented in vector notation. So top is 1 means complete probability of this state being in state 0, and 0 probability of being in state 1. All right. So in the very similar manner, I think now you can write yourself about state 1. So state 1 can also be written as the linear combination of state 0 and 1, right? Which will be equal to, so if I know that the state is 1, the final result is 1, that means 0 probability of um, of the state being in state 0. So that is why here it will be 0 and this will be 1. Okay, which in vector notation I can write it as 0, 1. So this is how state 0 and state 1 is represented, and all other states can be also written in this manner. Just the thing is that the value of alpha and beta will be different. So this was all about today's lecture, that is about quantum states. I hope everything is clear to you. Thank you.